Welcome back to Electron Devices and Circuits lecture video series. In this video we are going to discuss about the topic full wave bridge rectifier. At the end of the video you will be able to understand what is bridge rectifier, operation of bridge rectifier with its waveform and some solved problems related to rectifier. We will see the topics one by one. First one is a bridge rectifier. So we have already discussed half wave rectifier and full wave rectifier. Bridge rectifier is another category of full wave rectifier, whereas here 4 number of diodes are used which is connected in the form of a bridge, and this also utilizes both positive and negative half cycle of the input AC voltage and converts it into a pulsating DC. Since the 4 diodes are arranged in the form of a bridge-like structure, it is called as a bridge rectifier. See the circuit diagram here. So this circuit diagram comprises of input AC signal, one transformer and 4 diodes connected in the form of a bridge structure. The diodes are D1, D2, D3 and D4 and load resistance RL. So this circuit connected as per the structure given. And as here, so whenever the AC signal is applied to the diode, so you know AC signal normally comprises of both positive as well as negative half cycle. Assume the AC signal will be like this. So this is positive half cycle, this is negative half cycle. During the positive half cycle of the voltage, so what happens here? So this terminal is positive, this is normal transformer, not center tap. This is upper terminal is positive and lower terminal is negative. This positive terminal connected to the diode D4 and D1, whereas this positive supply polarity forward bias the diode D1 and reverse bias the diode D4. Similarly, this negative polarity is applied to this junction and it is fed to the diode D2 and D3. So this negative polarity forward biases the diode D2 and reverse biases the diode D3. So during positive half cycle we can say the diode D1 and D2 is said to be in forward bias and D3 and D4 is in reverse bias. So forward bias it acts as a closed switch. So see the current flowing direction, the current flow starts to flow from positive polarity. So here the current is flowing in this direction for during positive half cycle. Here the current reaches one junction. This diode is what? Reverse bias. So the current does not prefer this path. The current flows in this path. So the current starts from terminal A, takes the diode D1, and here again another junction. This diode is reverse bias, so it won't flow. So again the current flows through the load resistance RL in downward direction, and again it is coming in this direction. See here again one junction. This line, the current diode is open, so current will not flow. Again the entire current flows in this direction, and again the circuit is closing here because this is also open. So the current is flowing in this direction and again it is returning back to the supply in this way. So see here the current flowing direction is starts from here, takes this diode path and again flows through this resistance, and again it is coming here and takes the diode path D2, and again the circuit is closing in this way. So this is the direction of current flow during positive half cycle. Similarly, during negative half cycle, what happened? This thing gets reverses. Now the diode D1 and D2 reverse bias and D4 and D3 forward bias. This is because the terminal A is negative and terminal B is positive. This positive forward bias the diode D3 and reverse bias D2, and this negative forward bias the diode D4 and reverse bias D1. So now the current starts to flow from B terminal because B is positive. So current flowing direction will be, so see here we'll change the color. Color is not possible, just highlight. So the current flowing direction starts from the point B, again it goes in this way and it takes the path diode D3. So the diode takes the path D3, and again D1 is reverse bias, so it is open, so current never flows, and again it is flowing in this direction. Again it is coming here and diode D4 is forward bias, and again the circuit is closing in this direction. So it got closed to this way. So now the current is circulating in this direction. So either during the positive off cycle or during the negative off cycle, the current is flowing in the downward direction. So unidirectional. So when you tap the voltage across RL, this terminal is positive, this terminal is negative. So we can able to tap a unidirectional current which is same as that of the center tap rectifier. Got it. So this is the operation of the rectifier. So here also both the half cycle got utilized effectively. So the transformer utilization factor is similar to that of half wave rectifier, and almost all derivation parameters is same as that of the full wave rectifier. So whenever it is asked to explain bridge rectifier and derive the parameters, you can draw the circuit and explain the waveform which is similar to that of full wave rectifier, and also the derivation similar to full wave rectifier center tap. This also suits for bridge rectifier also. Whereas this is the bridge rectifier circuit. When you purchase it in the shop, you will get a device like this with 4 terminals, 2 terminals for input and 2 terminals for tapping the output. See here at this junction, so at the top junction and bottom junction input is given, and the left side junction and right side junction output is connected across the load resistance RL. Okay. So the next, this is the waveform. This waveform is very similar to that of full wave rectifier. Only one thing is what it is given means first waveform shows when diode D1 and D2 is conducting, and second waveform shows then diode D4 is conducting. This diode conducts for positive off cycle, so we will get only positive waveform, and this diode conducts during negative off cycle, but since the current flowing through RL is in same polarity, so negative off cycle also you will get the positive voltage. And this is the waveform, and this is the load current flowing. Whatever may be the diode, the load current is flowing. So here this is not only for when D1 and D2 is on, even when D3 and D4 is on also, D3 and D4 is on also, you will get the same voltage. So this is the load current, and this is load voltage. You will get the same waveform when D3, and here also you will write D1 and D2, D1 and D2 on. Got it? This is the waveform, and expression, as I told you, this is very similar to that of center tap rectifier. You refer that derivation. And advantages is here there is no center tap. So no center tap means cost will be somewhat less. And DC component is also 0 because the net resultant component cancels. So positive off cycle, the current is flowing in one direction, negative off cycle, see here, positive off cycle, the current is flowing in a downward direction through the transformer, negative off cycle, current is flowing in the upward direction. So the net resultant current in the transformer secondary becomes 0, so no DC saturation losses will happen. And transformer also utilized effectively. Peak inverse voltage shared across 2 diodes. This is because when you calculate the peak inverse voltage, 2 diodes are in series, because at a time 2 diodes are conducting. For positive off cycle, D1 and D2 is conducting. So we know that peak inverse voltage in center tap is 2 ESM. Now instead of one diode, here you are having 2 diodes. So ESM voltage gets shared between 2 diodes. So 2 into ESM divided by 2, you will get ESM. So peak inverse voltage is ESM. Size is also small, cost is also less. And only disadvantages is 4 diodes. Due to the presence of 4 diodes, internal voltage drop across the diode is 0.7 into 4 it will happen. So because for one cycle 0.7 into 4, for half cycle 0.7 into 2. That is only the drop, but this drop is considered to be very less. It is least bother. So we are using bridge rectifiers. So compared to center tap and bridge rectifier, which is widely used, means almost in all applications, bridge rectifier is versatile compared to that of center tap rectifier. So for even for low power and high power applications, everything power electronic applications, for all power supply designing, we are using mostly bridge rectifiers. And this is the comparison table for all the 3 rectifiers. So what are all the parameters we have derived? So this is the consolidation. So this will be easy for you to remember. And the next one is this is on bridge rectifier circuit. So you need one transformer, simply 4 diodes, 1 capacitor for removing unwanted AC component, and this is Zener diode. This is mainly for stabilizing the voltage at the output. Whenever there is some more fluctuations, we can use the Zener diode to get a constant output, and 1 LED. When you connect a circuit like this, so this will be the practical circuit will be looking like this. So when you connect a circuit like this in breadboard, and if the LED starts to glow, this is a perfect design of full wave bridge rectifier. You try at your home. Simply you need the components: one breadboard, a transformer, and 4 diodes, capacitor, Zener diode, resistance, and LED. So with this we can able to develop a rectifier circuit. See, and the next one is the problem. This is a very simple problem. A full wave rectifier using 2 diodes having a maximum voltage of 18 volts. Full wave rectifier with 2 diodes, maximum voltage of 18 volt across full secondary windings as the input. That means we can take the input as 18 volt, which is nothing but the full wave rectifier using 2 diodes. That means this is a center tap. Maximum voltage. That means maximum voltage across the diode. When you will get maximum voltage across the diode, which is nothing but peak inverse voltage. What's the formula for peak inverse voltage in center tap? 2 ESM. So 2 ESM equal to 18 volt is the given data. Calculate peak inverse voltage for the diode. Peak inverse voltage for the diode is ESM, 1 ESM equal to 9 volt. So 2 peak inverse voltage is nothing but 18 volts. So this is given the data itself, you are having an answer. Right, so you have to understand this sentence properly for giving the answer. Maximum voltage is nothing but peak inverse voltage. So 2 diodes it is given. Normally full wave center tap rectifier formula itself 2 ESM. So with this nothing but the voltage across 2 diodes. So this becomes 18 volt is the answer. And the second problem is what is the necessary AC input power from the transformer secondary used in a half wave rectifier to deliver 500 watts of DC power to the load. So DC power PDC equal to 500 watts. Any other data? No. What would be the AC power input for the same load in a full wave rectifier? Data is given for half wave rectifier and the required data is for full wave rectifier. So what you have to do here for half wave rectifier, what is the thing you know? Efficiency. It's nothing but 40.6%, you know, so keep that in mind. So what you have to find out means AC input power for the same load in full wave rectifier. So first thing you have to calculate AC input power for half wave rectifier and AC input power for full wave rectifier for the same load. So we will see how this can be executed. So PAC for half wave rectifier is percentage efficiency, you know, PDC by PAC into 100. You know, efficiency 40.6%. PDC is given. From that PAC is calculated. So this becomes how much is this value? PAC is equal to 1.2315 kilowatt. So here one point is given that for the same load in full wave rectifier. So whatever the load we have considered in half wave rectifier, same load we have to consider for full wave rectifier also, but for that we have to calculate AC input power. So for same load means, you know, full wave rectifier efficiency formula, you know, efficiency PDC by PAC is the formula. PDC is 500. This is because it is given as load is same. Here the load is taken as 500 watts. For the same load means the same amount of power will be delivered. So for full wave rectifier also we have to use the same amount of power for DC power. So we have to consider same 500 here, and from that PAC you need to find out. So from this PAC value is 0.615 kilowatts. So this is the answer for the second problem. Is it right? See, so at the end of this video you came to know about the operation of a bridge rectifier and how to solve the problems using rectifier formulas in half wave and full wave rectifier. So hope you understand the concept clearly. Meet you in next video. Thank you for watching.